I think we can get started. Hello, everyone. Thank you for being here in person and on Zoom for another Kent lecture. Today we have Charlie Greer. He's a professional engineer and has been an adjunct lecturer for the CE department at U of I. Since 2016, he has taught the case histories in infrastructure engineering, both in the classroom and online, which is open to senior and graduate students. Actually, we got the news that Professor Greer is going to be
Adjunct lecturer.
sorry. Is going to be teaching the class this summer for everybody that's interested. He earned his bachelor's and master's from U of I, from 1971 and 1973. And he has a research assistant. He was a research assistant and worked on the development of resilient modulus testing equipment for Illinois soils under Professor Marshall Thompson, who is online right now, which is a very cool guy. He served 8 years in the U.S. Army Reserve as an officer in the Corps of Engineer branch and was on the commander's list for his engineer officer basic course in Fort Belvoir. He was discharged with the rank of captain in 1979. Greer started his professional career with Law Engineering Testing Company in Atlanta, Georgia in '73 and retired in 2015. There he rose from staff engineer to corporate director of engineering. During his career, he worked on a wide range of civil engineering projects around the world. This included the evaluation and recommendations for the rehabilitation of 100 miles of highways in Costa Rica, repairs of a runway in Barbados, the evaluation of a cargo distribution center in the Cayman Islands, the rehabilitation of a runway in Turks and Caicos, the evaluation of concrete strength issues for several high-rise residential buildings in Hong Kong, the construction of a multi-use high-rise development in Shanghai, China, and a large bus maintenance facility in Canada. He also worked on numerous projects throughout the United States. This included many projects at the Hartsfield-Jackson Atlanta Airport from '74 to 2015. The projects included quality control and inspection for the reconstruction of runway 9L at '74. The runway, which consists of concrete, is still in service and has served an estimated more than 8 million departures as it nears 50 years in service. Other projects include engineering evaluation, design and construction inspection, and testing for the Meadfield expansion in the mid and late '70s, which included a 1.25 mile long underground people mover along with 18-foot diameter tunnel, 18 feet beneath an active runway and taxiway. He was also instrumental in the development of payment management program for Atlanta. This program, performed every 3 to 4 years, has utilized numerous innovations in pavement evaluation since its inception in 1984. The program, considered one of the most comprehensive in the world, is credited with extending the life of 2 main departure runways by more than 20 years beyond their original design life. This has saved Atlanta an estimated of $100 million in capital costs, along with significant positive impacts on the environment to reduce construction activities. Our speaker today was also involved in the investigation, analysis, design, and construction for the move of 2 nuclear reactor vessels across 46 miles of state, county, and private roads in the Northeast Tennessee for the TVA Phipps Bend nuclear plant. Each vessel weighed 2.1 million pounds, and the transport trailer system had 24 axle lines with 16 tires for each line, for a total of 384 tires. The total vehicle weight was approximately 3 million pounds. Here's technical publications and presentations on a wide range of civil engineering projects, problems, and issues number more than 100. These have been presented to numerous technical conferences around the world in Norway, Sweden, Costa Rica, Canada, Hong Kong, New Zealand, and England, and across the United States. He served and has served on several technical committees for TRB, ACE, and ACI. And his awards and honors include the U of I C.C. Wiley Traveling Award, the Engineer of the Year in Georgia from the Georgia Society of Engineers. He is an honorary member of the International Society of Concrete Pavements, and he is the awardee of the ASC's prestigious award, the Bohr and Jeff Award. He also has the GSP or the Lifetime Achievement Award in Engineering from Georgia, which is where GSP is from. And he is currently he's a registered professional engineer in Georgia and Florida. So today, very honored to have introduced him. We should all welcome our speaker, Charlie Greer.
Thank you, Javier. If I had known you were going to go through the whole thing, I would have made it shorter, but anyway.
I think it's important for us to learn about.
When I agreed to do this talk, first, I thank the center and the department for giving me a chance to talk to you today. And what I was going to do when I start putting things together was going to talk about this pressure reactor vessel move that we made back in 1979, 80, and 81. And then the Cape Hatteras Lighthouse relocation that we did in the late 90s. However, the time frame was such that I had to reduce it down to just a pressure vessel today, which hopefully you'll find of some interest. And we'll see a couple of slides on the lighthouse, and you can see more on these if you want to come to the CEE 498 CH course this summer. So anyway, without further ado, talk about, from nuclear reactor pressure vessels to a lighthouse. As I say, part one. Part two will be some other time to be determined. But, I consider it a warm-up project for the lighthouse project. This was 3 million pounds. The lighthouse was 10 million pounds. So it was kind of a practice project for that. And so a contractor comes to you, you're senior engineer, you're sitting in your office and says, hey, we've got to move 2 nuclear reactor pressure vessels from Knoxville, Tennessee, the TVA's Phipsbend plant up in Northeast Tennessee. You say, wow, that'd be a lot of fun. He says, oh, by the way, we got to say things weigh 2.1 million pounds, and we've got to get a permit from TDOT in order to move these. It's a little bit heavier than your normal weight. And so you talk about the schedule. Year one, you're going to evaluate, determine what requirements are required to upgrade the infrastructure. And then in year two, they're going to move the first vessel and the associated equipment with that. And then in year three, you'll move the second vessel equipment and do any damage assessment if need be. So you're hoping there won't be any damage, but it'll be assessed in year three if you do. And so the route, if we look at the route, you talk about the route, the first leg is 26 miles overland. It goes from Knoxville up to here. Then it goes back in the water for 35 miles on barge, and then comes back out of the water and goes the last 20 miles up to the plant. And part of the reason for in and out of the water was the river couldn't be counted on to have enough draft to be able to get the thing moved. These were fabricated in Memphis, Tennessee, which is far west Tennessee, and barged on the Tennessee River up to Knoxville. So the little bit of history on that. Things that you're worried about when you talk to the contractor, well, you're concerned about slope stability. Northeast Tennessee has a lot of hills, so you have a lot of cut slopes and fill slopes that you're worried about. We're going to drive 3 million pounds across it. What's that going to do to the slope? And to give you a feel for what this is like, it's like taking 10 feet of fill and moving it down the road. That's what you can equate this to. When I work on projects, I always try to think of what are some things that I can relate it to give a better feel for what I'm really doing when we're doing these things. Okay, and then you're going to be concerned, obviously, about underground utilities, culverts, pipes, and things like that. Pavement design. Pavements are designed for millions of pavements. I know when I was in school here, designed for 1 million equivalent single wheel loads during a lifetime was a lot. Now you're looking at tens of millions of things, and not 20 years of life, but 40 and 50 years of life. So things have changed. But you're only going to have 2 moves with this thing. And the contractor has already won the bid. In other words, he's got a $12 million lump sum bid to move these things from Knoxville to the plant site. So you're constrained in your money as well as the time issue. You're going to deliver them to TVA's front door, and then TVA will take the vessels from there. But you're responsible for these state, county, and private roads and getting a permit from PDOT. So what are the objectives? You know, you talk to the contractor, it's the same thing you always hear: on time, on budget, and no damage. That's what the contractor. What are you as a consultant concerned about? Well, slopes, underground utilities, where are the pavement sections, what do they need to be? And the bridges. You know, this has got to go across the bridge. And most of those aren't designed for 3 million pound loads cost. And this is what it looks like. This is the first vessel here, and you can see this is the vessel itself here. And then this is part of the frame that holds it onto the trailer system. And you've got all these accessories that come with it. The heads for the reactor, the shroud heads, and you can't go under all of the overpasses along the route. So you got to come off and round, and so sometimes the route gets pretty curly. So you say, okay, what's the transport system look like? Well, it's a trailer. It's 2 sections. The front section is modules. You see 6 of them there, 2 by crossed and 3 in length. There are 4 axle lines on each one. So that has 4 axle lines, and then there are 4 tires, 8 axles. I'm sorry, 8 tires per axle line. This being an axle line, and then we have coming across to the other module is the rest of the line. The rear section is essentially the same, except it's a 2 by 2 module, 6 axles instead of 4. And each axle line, as I say, has 2 dual wheels on the end. And these are 8 1/4 by 15 Michelins, but they're not the kind of Michelins that you'll see on your car. They're a little bit different for that, as you'll see. And any of you that have been involved with ABC, accelerated bridge construction, where they build the bridge near the final resting spot, and then they move it into place all in one fell swoop. Well, a lot of times you'll see these kind of trailer sections used to move that bridge components into place. Okay, so we get it all together. We say, okay, we've got the vessel on top of the trailer system. We've got 12 axle lines and 16 tires in each section. For the 24 axles, 384 tires. So, you know, it's kind of like, I think it was, now I can't think of his name, but the Greek guy said, you know, give me a lever, a place to stand, and I can move anything with the lever. This is kind of the same way. If you give me enough tires, I can move anything, okay? So the length's about 130 feet, rear tire to front tire. And the outside is 25 feet wide, outside of tire and outside of tire. So even on the 4-lane divided state route, this is going to hang over onto the shoulder. And the height is a little over 30 feet. So you're not going to go under the power lines either. They're going to have to be raised and lowered, and those were actually moved temporary. So as you start to think through the project, your little pavement design, that's what I call it, there's a whole lot of other things you've got to be thinking about out there, particularly if you're the project manager and places that you've got to interface with. So if we look quickly at the details of the tire spacing center to center of the duals is a little under 11 inches. The center to center spacing of the entire interior tires is 21 inches. The axle to axle on a section is about 7.5 feet. And the interesting thing, and this is what was really beneficial, the spacing between axles was a little over 5 feet. And so we'll see that that's an important aspect later on. And as I said, got to raise and lower utility lines, can't go under overpasses, things like that. So just in summary, when you get it all together, you've got a weight just under 3 million pounds. We're going to use 384 tires. These are 8 1/4 Michelins. Their tire inflation pressure is 124 PSI. So you can see these aren't your typical car tires. They're beginning to impinge on what you would see on aircraft tire pressure, although they're smaller than those. And the load on each tire, the front is about 7,600 pounds, and the rear is about 7,900 pounds. This is just another shot of it when it's up and ready to go. You see, you've got a driver at the front end and one you can't see back here at the back. So you say, wow, we got a driver on this thing, 2 of them. So you look at it and say, okay, how are we going to move it? We've got the vessel up on the trailer. How do we move it? Well, we're going to pull it with 3 tractors and push it with 2. And the contractor had 2 options for the tractors. One was a Mack and one was a Michigan. This is the Mack one here. It's a 4-axle single tire, 38 PSI on the tire inflation. So it's kind of high flotation. The axle spacing is about 8 feet, tire spacing is about 8 feet. The axles are just under 6 feet. The Michigan tractor is a 2-axle single wheel, 24,500 pound wheel loads at 34 PSI. And the spacing is about 9 foot on the tires and just under 11 foot on the axle spacing. The contractor ended up selecting the Michigan. And the reason I think is that the Michigan with 5 Michigan tractors, it's shorter than if they had 5 Mack tractors. And you remember, you're going to have to come up and go around corners of intersections in these roads. It's not like you've got this nice 150-foot wide runway that you can go down. You've got some roads that, as we'll see here, aren't even wide enough for this, that you're going to have to upgrade. So this is what the Michigan looks like in place. This is pushing here. And as you say, not quite 25,000 pound wheel loads. So those are pretty hefty on the pavement too. So how do you make turns? You know, this is actually going into the page here. But if you were coming out, each axle articulates independently. So as you come up and want to come around that corner, the axles turn as they need to, and we could bring it out here and drive it through the parking lot if we had a need to. There's not a need to, fortunately, but we could do that. And the pavement might be sufficient. It might not be. We'll see. Okay, so as a consultant, what are you going to do as you go through trying to figure out the pavement design? We're going to concentrate on the pavements and not only talk about the slope stabilities and culverts and like. But you're going to do a site reconnaissance. In other words, you want to drive this 46 miles and see what's out there. What can I get for existing construction information? What do I think is out there? Then you're going to come in, core the pavements, drill soil test borings, do field testing, lab testing, do your high powered engineering analysis, and then validate the design procedure. This is a key issue. Or as you go through a design and you're all ready to go, how do you validate or get confidence that you think it's going to work? Okay. And I'd ask Jordan, but he already knows. Then quality control during construction to be sure that it's being built the way it needs to be. Go and observe your projects. See how they perform so that you can then put that into your engineering judgment as you go through your career, okay? And then we'll evaluate any damage claims, which hopefully there aren't any, but we'll see. Remember, this is 46 miles. That's just under 250,000 feet of pavement. We're not going to catch every little thing out there, but this thing will, okay? Okay, so, you know, we go through, we review our plans, we do our site reconnaissance, we look at slope stabilities, and we see what some of the slopes are like. And we see there are some pretty good slopes here. And yeah, we're pretty close to the edge at the top on these things. So we've got an issue with that. Culverts, we've got shallow culverts, as you see on the left. We've got deep culverts, as you see on the right. And then we've got one here where everybody's standing around looking at the culvert and the vessel. And we'll talk a little bit in a while about why they're all standing there. Okay. So the roads, most of them are good. Most of this route was on state roads, which were 4-lane divided, semi-limited access, not interstate standard, but pretty good. And you can see there that the roads are pretty good, but some of the roads you're going to go across aren't so good. This is a county road, well, not wide enough. Looks like it's already failing with the county traffic, let alone we're going to haul 3 million. Let's cost it twice. Okay. Okay, and these roads exist, with the exception of some access roads to get off the docks and up to the industrial parks. All the roads are existing, so they're asphalt surface now, in service, and they're to remain in service after you make the moves, okay? So what do you propose to do to evaluate what's out there beyond your drawings and as-built and all that? You know, you look at your drawing, everything's nice and neat, perfect little pavement sections and the like. So we say, how are we going to do that? Anybody got any ideas on how you would do that? I do class questions in talks. No ideas? You're just shy, I know. Well, we're going to cut cores. And so we cut cores of the pavement to see how thick is the pavement section, the asphalt, the crushed stone, or whatever's out there. And we get our cores and we line them all up. We say, wow, this isn't as nice and neat uniform as we thought it was, okay? And just for historical purposes, neither one of these photos are from this project. This photo here is actually from the LTP sampling program in the southern region. The first core was actually back here. I took it to be able to cut it up and give a copy or cut section out to some of the members of the thing. But this is the first section that was tested in LTPP in the southern region. These happen to be from a runway where we thought we had all of the thicknesses pretty well defined and pretty uniform. You see, not the case. So just because you look at the drawing doesn't mean what's out there, okay? So you're going to also drill borings. You're going to do undisturbed samples. You're going to get the sample and test, but you're also going to do what's called the standard penetration test. Anybody in here know what the standard penetration test is? Okay, a couple of people do. Geotechnical engineers know it well. It's been around for a long time. You have a split spoon sampler that you're driving into the soil with a 140-pound hammer, dropping 30 inches. And you count the number of blows, you seed it 6 inches, and then count the number of blows to drive it 12 inches. And that's the standard penetration result. Okay, so you're going to do boring. How many would you do? You got 46 miles, couple hundred. Anybody vote for 200 or more? Anybody vote for 500? You vote for 500? Okay, okay. How about 49? They say, why 49? Okay. Well, kind of simple. We looked at, well, where are we going to do them? Traveled way or the shoulders? We've got traffic control issues. So on the state roads, what we did was we drilled and cored in the shoulders. And if the shoulder results matched what was on the drawing, we assumed that the traveled way for the highway matched what was on it. Now you can pick at that all you want, but that's what we did. And fortunately, I'm here to tell you, so it must have worked, okay? The county and private roads, obviously, you're going to drill in the traveled way. Because if you remember the county road, there's only about 1.5 lines of pavement there anyway right now. How deep? 10 feet. That's about what we're looking for the pavement. We're going to go deeper if we've got issues with slope stability and things like that. And samples we've talked about, standard penetration, undisturbed. What did we find? Well, interesting. For the state roads, we found about 15 inches of asphalt and over 12 inches of crushed stone over subgrade. Looks like this. For the private roads, the industrial routes and the like, we found 4 inches of asphalt over 8 inches of crushed stone. That's not too bad. That's what you typically would find in Northeast Tennessee for industrial type pavements and the like, with the kind of CBRs that we'll talk about. The state road or the county roads, though, 1 inch of surface treatment over 4 inches of crushed stone. And you remember the one you saw, so we're saying, I don't think the county roads are going to cut it here. And we have one very short section out of this thing, about 200 feet, that had concrete pavement. And we said, well, we're not going to mess with it. We'll go across it. If there's any damage to it, we can replace it, and it's not a big issue. Okay, so what else would you propose? Anybody got any ideas? What would you supplement all that drilling and coring with? Ever heard of CBR test? The California bearing ratio. You thought you had long forgotten it, right? It's kind of like, now standing here in front of one of the most august research groups in the world, and I'm talking about a test that's 80, 90 years old. But always remember one thing. If it worked in the past, it'll probably work today, okay? So never forget what's out there in the past. There may be times when you're like, just like the Binkelman B, We have the fancy falling weight deflectometer. We've been using it for almost nigh on 40 years now. But every now and then we go back to the good old Binkham and beam developed in the Washoe road test in 1952 because we can get some information quick and carry the beam in a car or fly it on a plane to get it there. Can't do that with the FWD. Okay, now we're going to perform lab tests? No. We're concerned about what's actually out there in the field. So we're going to perform the test down the boreholes in the field, in the top of the subgrade with the current conditions that we have. How many would you do? Somebody give me an estimate of what you would, how many tests you would perform. We know we did 49 borings.
So 49.
Huh?
49.
49, okay, well, that's a good toss. How about 42? Now you say, why 42? You know, why not 50 or 60 or 20? Well, when we looked at it, we identified from the borings and the plans and everything, about 26 different sections of pavement out there. And most of it based on time of construction, things like that. So we said, well, that'll give us 1 or 2 per section of roadway. And we'll do more in these county roads, a closer frequency in the county roads than the state roads, because the state roads are much better, as we'll see. We already know they're 15 and 12. That's going to be pretty good pavement, we hope. And time and money. You got time issues to do how many tests you want, and money. Remember, contractors already bid the project. He's going to get a fixed $12 million for this move. So every dollar you spend is a dollar of potential profit that the contractor could have had. So he's going to want you to do the bare minimum, and you're going to want to do as much as you can so that you can sleep at night, okay? Okay, so you got to find that balance. So these are the 42 CBR tests. We say, well, why didn't you look at them in each section? We said, you know, we're going to take the whole route as a whole for the subgrade and analyze it that way. You can argue it both ways, but again, this worked, and we'll see here. So how we analyze it, draw up a nice little histogram of the data, whatever it is. And we see that the median is about 6 to 7. That's the value that half the data is above, half the data is below. And so we say, oh, that looks okay. So do we use the median? Do we use the maximum value, or do we use the minimum value? There's where your judgment comes in. You know, you've got whether you're doing with CBR equation or a nice big fancy finite element program, what are your inputs? And Marshall Thompson always told us, you know, a lot of times we're sitting out here measuring something with a micrometer that we marked with chalk and cut with an axe. And we're measuring it with our micrometer. So always think about, what are you doing out here? What are your inputs? So we look at that and we see that the average CBR is about 8.3, standard deviations is a little under 6, and that's a coefficient of variation of 70%. That's fairly high. And we said, you know, we're going to turn our sampling equation around. You know, we can, if we know this coefficient of variation and the error that we're willing to accept, we can calculate how many samples we need to take. Well, here we know how many samples we took, and we know the standard deviation, which gives us coefficient of variation. So we can find that, well, the error in that answer was about 21%. So 8.3. So my error at 95% level of confidence is about 1.5 of CBR. They said, but you know, looking at the test 41 and 42, those look to be not realistic for the average. So we're going to throw those out, and we now have an average of 7.3, standard deviation 3.6. And if you look in ASTM, there is a procedure in ASTM for discarding outliers. So you can actually go through a process to calculate it. But as Ernie Berenberg always said, my engineering judgment tells me I should get rid of 21 and 34. Okay, so we do that. Now our average is 7.3, standard deviation 3.6. Coefficient of variation is still pretty high, it's 49%. But our error is down to 15%. So now maybe our error on the 95% level of confidence, we're within 1 on the CBR average, okay? Okay, what we end up saying is we're going to pick a CBR 5. That's the 75th percentile value. In other words, 75% of the data is above that, 25% is below. Does that mean we have a 25% chance of failure? No. If you look back at most of the designs and look at where they drew all these design curves, you'll see they were pretty conservative when they drew the curve. And so you're going to have a nice line that you're going to calculate. You really should be using a big wide paintbrush, okay? But anyway, moving ahead. So it's a case of how much risk are you willing to take and how much risk is the contractor willing to take? And oh, by the way, we still have that CBR of 1 out there, okay? But we'll deal with that a little later. So when it comes time to do the evaluation, we said, wow, South Africa has done some big heavy moves with equivalent single wheel loads. Corps of Engineers has a procedure for that. So we'll use a good old CBR equation. They've had this modified several times, but this is the one that we used. And so the thickness of the total pavement above that subgrade of CBR 5 is a function of how many times I'm going to go over it, what's the load, what's the pressure, and what's the strength of my subgrade, okay? So you can go through that and see. We also found in the Highway Research Record Board a paper about 5 years earlier transmitting heavy loads over pavements. And this is how to turn multiple wheels into an equivalent single wheel load. So we use this curve to take those tires and convert them to a single tire. So we look at the Michigan, we come up with, we take tire A, we look at the effect of B, C, and D. It adds about 3%. And so our load, the equivalent single wheel load goes from 24.5 up to a little over 25.3. We look at the trailer, and we're assuming in this that the contact is a circular. That's not exactly correct, but you're going to find a lot of times you got to make simplifying assumptions when you get out in the real world. So when we look at the 4.5-inch radius, the axle spacing is 63 inches. We're 14 radii between the axles. We're off the chart, no effect axle to axle based on this equation. So no impact from those. And each axle then becomes a single pass. So one move, 24 axles, at the second move, 48 axles go across to 48 tire loads. So say, okay. And then we go through and look at what's the impact of the spacing of the tire. And we can go through all of those different ones and find out that it's about 2.5 times. So that 7,800, 7,900 becomes a load of about 19,800. We chose the rear one, again, being on the conservative side. The front trailer is a little less, but at some point you can be getting so fine grained on things that you lose track of where you're at, okay? So we say, the trailer is 19,800 pounds single wheel load. The Michigan's 25.3, it must be more critical. Just, looking at those numbers without going through the design yet. So we go through the design and we see, okay, the trailer, an interior tire is going to have 48 coverages. The Michigan is going to add 20 coverages, but it's a different tire load and pressure. And we got to look at the combined effects of those two. How do we deal with the combined effects? Well, we look at our subgrade, and we see we got to have a cover of thickness of T. Well, we're going to assume the crushed stone is CBR of 100. How much asphalt do we need over that? Okay. And one of the things you need to look at is when the CBR of the crushed stone gets to 48, the equation breaks down. The thickness of asphalt goes negative when the CBR goes above 48 on the crushed stone. So you got to understand what's the boundary conditions of these formula that you're using. So we go through and look at these. These are the parameters for coverages, loads, contact pressures, and we got to look at the combined effect, but we lucked out. When we did our curves for thickness versus the number of coverages, look at the map, which wasn't used, is a lot more coverages for each given thickness. The Michigan and the main trailer are almost identical. So we said, okay, for the Michigan, 9 inches is needed. For the trailer, 11 inches needed. And if I just say I'm going to add the 20 and 48 together, look at that, then I need 11.5 inches. So I'm just going to combine the Michigan and the trailer, even though it's not exact, but that's a conservative look at it. Okay. So we go through and say, well, we'll look at a factor of safety of 1. Pavements don't normally use factors of safety. You're designing them for a factor of safety of 1. You got a life of 20 years, 40 years, boom, you're designing it such you think it's going to fail at the end of 40 years. And the failure is not catastrophic typically, not like structure. We look at, well, we need 11.5 inches. Our county roads don't make it. Our private roads are probably okay. And then our state roads are way over the line, okay? But I said, hey, what if we have 14 inches? That gives us a factor of safety of 3. So we've got more than a life of just the 2 passes. And if we go to 16 inches, we have a factor of safety of 10. Okay. So now what I said is, okay, for the county roads, the private roads, the industrial routes, I want 14 inches. And for the state roads, I want 16 inches. Well, I'm in good shape because I already got 27 inches, 15 of which is asphalt. So, but the Corps of Engineer is irregardless, that's not a word, regardless of the thickness or the strength of the material above it, okay? So this would say 16 inches, whether it was all asphalt, crushed stone, or concrete. Now, common sense tells me that can't be right. But we look at what are we going to put in for the pavement? Crushed stone is our basic material. How much cover for that, and what should it be? So we said, well, when we look at this, we need a cover thickness of X. How much should the asphalt be? They said, you know, again, I look at what can I compare this to? And this is like moving 40 semi-tractor trailers stacked on top of each other, or 4 747 aircraft stacked on top of each other. They said, you know, we're not going to land a 747 out here, but we'll use a thickness that might work for a 747. So went to the FAA's procedures back in there, and they required a minimum on runways and taxiways 4 inches. They said, good. Our design will be 4 inches of asphalt, 10 inches of crushed stone for the private roads, county roads, and the state roads would be 4 and 12. Okay. And so, and then we can do a little design curve here for thickness versus coverages, because the contractor always has a better idea than you as the engineer did. And he said, what I want to do is put down 3 and 10, or upgrade to 3 and 10 where I need to upgrade. And after the second move, I'll put down the last inch. And these people will think they, particularly the county roads, they'll think they have interstate highway out. Okay. So he said, that's interesting. So are you comfortable with that? Well, you look in 13 inches, you have a factor of safety of about 2.2. You say, well, I guess, but never be afraid to walk away from value engineering or design change. You know, because once it's made, it's yours. You've bought it, okay? So always remember, the engineer doesn't always have the final say. Operational issues, a whole host of other things can drive that. So how do you validate this procedure? Well, Jordan, how did we validate it?
I think you loaded a truck with the load plates, right? Simulated a proof rolling thing.
Right. We got one section of module and jack the wheels up. I talk about these axles can go up and down 24 inches. So we jacked all the axles up but one. We left one just kind of skimming the surface for some stability. Put steel plates on it till we simulated one axle and walked 46 miles, watching how it did. One of the guys in our Knoxville office, Brad, probably weighed, I don't know, 250, 300 pounds. He was about 6'6". He walked the entire 46 miles, but I walked the last 8 miles with him because I wanted to see what we were seeing out there too, okay? Always go out and look at your project. So no problems on the state routes, and the county roads were beginning to crack up with just that single axle. So we say, okay, we know we're between the two bounds. Obviously, we need more in the county road, and the state roads are fine. So we're good to go. We move ahead. Whoop. So how did it go? Well, there weren't too many problems. The state roads are pretty substantial. That's not me, even though it might look like me when I was younger. But you can see you go right down the state roads. And today, people could come right up to this thing. This was the biggest thing to hit Northeast Tennessee back in 1980 that you could think of. Today, insurance and litigation would force the contractor to keep people much further away. Okay. So when you get out on projects, site safety, insurance, litigation are prime issues that you need to be worried about. To protect the culverts and conduits, the contractor used these ramps. Just pull up, drop them in place, the vessel moves over, no problem. And you can see here how the axles go up and down and just kind of walk over the bump in the road, so to speak. Here, you look at that and say, what's going on? Got a lot of people standing around. Well, one of the axles failed to retract on the very first day when it was going over the bump, so to speak, and blew a tire. And there was a lot of standing around for several hours while they got to crawl back into the middle. Obviously, it wasn't one on the outside that blew, it was back in the inside. So the contractor abandoned the ramps and with no problems. Now, if you remember back, we did the proof rolling with the single axle. We didn't use any ramps. And we went the entire 46 miles. So you already know that's probably going to be okay. Okay. So how can he do it? Like I said, the load is more spread out than the analysis model. So always look at your model and how good is it compared to what's going on in the field. And if your model doesn't give you the right answer, you probably have a wrong model. Okay. So proof rolling, we already knew that probably would not be a problem. There were problems along the way. You can see here, there's a little bit of heave in the shoulder, some shearing of the asphalt. This is only a 1-inch overlay, wet, not much bond in the industrial road here. And again, this is just another view of that industrial road and some of the pavement, just like icing or on a cake. Shoulder, you see on the far left, there's no shoulder over there. So the contractor's already a foot over onto the shoulder on the right, and occasionally you got some ruptures of that shoulder pavement. Go across bridges. Any idea how you go across that bridge? I know I'm almost out of time here, but I'm almost done too. Well, shore underneath. Very easy, okay? And this was interesting. This was the very first part of the route. They had to go under I-40, and they couldn't go under it. So they had to go build a temporary bypass that went down in the lower ground here. And you can see here now, we're just temporary. So we only use the crushed stone for the surface, okay? And this is what some of the roads look like once they were upgraded. And you can see that's a pretty nice road for a county road, okay? And you can see, you can imagine coming up here and making a right turn with that. Each axle just kind of, I call it scoots around the corner, so to speak. So what did TDOT do? We went to them, they said, well, we don't think your plan will work, but move it and we'll assess damages afterwards. Not a good idea. You don't know what the ground rules are and what's the penalty going to be. So, but you have no choice. Contractor's got the bid, contractor's got to make the move. You go and do the best you can. What they did for their evaluation, they selected 15 sections. They did elevations across the cross sections. Of the 15, one was not traversed. It was a control section, and 14 were actually traversed. Elevations across sections, Binkelman beam deflections, in-place density with the nuclear method, and then they also did thickness of the asphalt base. They did 1, 2, and 3 before the move and after the move. And before move was in May, after move was in July. We went through their data and they didn't correct for temperature, but it made a hypothesis that the deflections and the elevations before and after the move were equal. If I can't reject that, then I make the assumption that the move had little impact on the pavement. And that's what we were able to show. How would I do this thing differently today? There's a whole host of things that I would add to what I'm doing. Video recording, GPS, GIF, falling weight deflectometer, find those strong and weak areas of pavement so I can strategically locate the destructive test. I'm not just out there poking blindly, okay? Radar scans, seismic analysis, surface waves, continuous video, laser distress, no CBR tests. I probably still would perform CBR test. You know, if it worked in the past, it should still work. Maybe you get a handful of those for comparison. Go through your fancy analysis of today, compare it to the crude analysis of the past, okay? And always go out there and proof roll before you move it. And resilient modulus, layered elastic, use all that stuff to get it. I would do a falling weight deflectometer before and after the moves to see, and again, go out and observe what goes on. So you can see how does it actually perform. Oh, I keep going the wrong way here. And evaluation of damage claims. There was some damage claims. We don't have time to go into them. They were very nominal, about 1% of the project cost. But the contractor had not budgeted any damage claims. So that became an issue to talk about, okay? So, okay. I keep going the wrong way here. And this is an interesting, and I'll close with this. This is the road, if you look at the left here, the dock in Knoxville is down here, and they bring it up on a crushed aggregate base, and then they come out here into the industrial park. And the contractor, I would tell him, I want to be there the first day of the move. And live in Atlanta, this is in Knoxville. And so they kept saying, well, we're going to move tomorrow, but tomorrow never came. And finally, one day he calls a Saturday afternoon, says, hey, we're moving first thing Sunday morning, in the morning. So I went up to Knoxville, got a hotel, stayed the night, went to breakfast early, got a newspaper. It was the biggest thing, you know, the vessel comes to Tennessee, and there were ruts in the paper. And I'm going, oh no, this can't be. So I get out to the site, worried to death, and you see these little lines here. Those were the ruts. They were what the limestone aggregate had a lot of dust on it. And as this thing came up, the tires pick up the dust and they plastered it down on the asphalt, just like paint. And you could put your hand across that rut. There was no rut there. But to that reporter, oh, the pavements are rutted big time, okay? So anyway, the end, no. One last thing. The plant was canceled not long before the second one. Well, most of you weren't around when 3 Mile Island occurred. But the nuclear industry really tailed down after that, okay? And so the plant got canceled. You can Google Phipps Bend nuclear reactor pressure vessel and get some information on it. If you Google the heaviest load ever moved across in North America, which is no longer the case, but if you Google that, you'll get a YouTube, you should get a link to a YouTube that will show the actual move going on. Someone has posted that up. And like all good projects, the first RPV, they don't know what happened to it. I don't know what happened to it. And there's people arguing that the second one was never moved. Now, I didn't see the second one move because I went on to other projects. Our people in Knoxville took care of that. But like all good things, there's always a conspiracy about something. Okay, okay, so they were done minimums. Just to touch base on the lighthouse, 208-foot tall lighthouse, weighs 10 million pounds, founded on fine sands beneath the water table. It's been through numerous hurricanes, survived the Charleston earthquake of 1886. Most of you may not know that's the largest earthquake east of the Mississippi, rang church bells in Boston, they say. We've got to move it 2,900 feet across loose dune sand and the attendance facilities with it. And we've got to keep everything in the exact same spatial location when it gets there, but 2 feet higher. Now, when you read your contract, you can't do exact. You know, what's the tolerance? Think about tolerances on things, okay? Okay, I think I did go over a hand a bit. So, if there are any questions, I'll try to answer them. If I can't answer them, I have an assistant with me who will answer. Yeah.
Thank you for the very nice and intriguing presentation.
Thank you.
So I have a question that relates back to one of the starting slides. You talked about the objectives of both the contractor and the consultant. And you said the contractor was concerned about the damage in pavements.
Yes.
But the consultant was concerned about slope stability or something like that.
Yeah.
Is that like is the liability divided on different topics, or is it always on the contractor or always?
It depends on a whole lot of things, but if that slope fails and you're working for the contractor, know that the contractor is going to look at you. And and even if you're working for the owner, the contractor is going to look at you and the owner may look at you. So you have to understand what's your responsibility in a contract, and things are changing. In the old days, as I call it, we had design, bid, build contract, where a designer designed a contract. It then got bid to contractors who it's awarded to someone, usually on low price, and then it's constructed. Today, there's a move to design build, where the engineers, the designers are part of the contractor's team. And so the owner likes it because they can say, there's a problem, you know, it's one of you two. It's not this kind of thing that might have been in the past. And as an engineer, you have to totally change your mindset. You're now working for the contractor, not the owner. And so the contractor's got different objectives than what the owner does. But you also have to remember your basic objective is protection of the general public. So you can't cut corners too far, or you're going to put the public at risk, and then you're at risk. So, but litigation is, even researchers get litigated, unfortunately. Other questions? Don't be afraid to ask questions. Yes.
Thank you so much for the presentation. So you mentioned at the very beginning that the contractor actually didn't budget any cost regarding damage. So that was the main concern they had. So how did you quantify what was the damage that was going to be the consequence of this operation, if any? Because
Well,
you mentioned that the TDOT wasn't that convinced at all with the plan. So I think it may have to be related to that.
Yeah. Well, there's an interesting story behind that, and I only have the part that I know. A couple of years after the move, I got a call from the contractor to come to a meeting with the Tennessee DOT. The contractor, as I remember, had filed a irrevocable letter of credit with the banks. And what that is the contractor put up $120,000 letter of credit with the bank that the contractor couldn't take back. But the DOT could reach in and get it for damage. So we went to a meeting and we talked for 4 hours, back and forth. The DOT was explaining what they wanted. Contractor was saying, no, I didn't. He knew he damaged some stuff. I mean, you can look at the pictures and say, there's some damage there. The DOT, if I remember right, wanted $96,000. So that's within the letter of credit. So they could have just reached in and taken it. But we had the meeting, back and forth. The contractor, I remember, he backed away from the table, you know, and I'm sitting there with him because I guess I'm on his side, but I'm there for the truth, okay? And so he writes down 96, which is what the state wanted. And he wrote down 32, which I guess he was kind of up to 32. Added them together, divided by 2, and offered 64,000. Well, about 2 hours into the meeting, a third person had come in, didn't say who they were. When you're in a meeting, always find out who's in that meeting. For 2 hours, the contractor's bearing his soul, if you will. This is an attorney for the DOT. And so at the end of that meeting, the attorney said, well, we're not prepared to accept 64,000 today. We'll let you know back. Well, this was the Wednesday before Thanksgiving. On Friday, the contractor told me that the DOT called him and said they were going to take the entire 120,000. Okay, so which they could do. And so they're going to file that on Friday, but it was a holiday and the person that would do the paperwork was off. And the letter of credit expired on that Friday. Now, I don't know I know nothing beyond that point, whether the contractor ever paid anything or what. But one issue was when somebody comes into a meeting, find out who they are, okay, for sure. Because it was an attorney, especially if it's an attorney. And then, you know, just timeliness is everything. You know, they handed the paperwork to whoever was going to call the bank, say, hey, ship us $120,000. They weren't there. And on Monday, it was too late. So timeliness, I talk about timeliness in this class. So I teach, It's everything. Okay, somebody else had a question? Yes,
I think we have time for the last.
yeah, just tell me when to shut up.
So I'm assuming it wasn't possible to assemble the vessel on the construction site, so this was the only realistic way that you could move it from.
Right, they were fabricated in Memphis, I don't know if you know where Memphis is, but it's way on the Mississippi River. They then barged it all the way to Knoxville, and then they had to go across land to get there. They couldn't trust the rivers the whole way, and I don't think the river went the entire route that they needed, so they fabricated them, barged them to Knoxville, and then they had to haul them across to the plant site. There would have been, I guess you could have set up a steel plant on site and done it, but the cost would have been prohibitive, obviously. And then what do you do with the steel plant after you do it? It's not like a paving job out here where a contractor will set up, a concrete plant or an asphalt plant on the project site if it's big enough and work, and then they take their plant and haul it to the next project. But steel fabrication plants, they're not very portable.
So fast forward to today, if you want to move something that big or even bigger, do they still do it like by land, or do they do it on rail, or do they bring in some helicopters? I don't know.
Well, it depends on the conditions of where you're at and what you're trying to do. If you look at if you take the course, or if I come back for part 2, the lighthouse was moved on for lack of a better word, a special rail system that was consistent of I-beams that were turned into what we call track beams. But it was moved overland because everything was overland for it, and it was only 2,900 feet. Like I say, the ABC, the accelerated bridge construction today, a lot of those, they're building the bridge component right there next to the site. If you watch the unfortunate tragedy down in Florida International University with the collapse of that pedestrian overpass, they built that with the accelerated construction right there, and then moved it and set it in place, and it works great, except they had a whole host of issues, which they're still design issues, construction issues, which are trying to be sorted out. And when you move something like this, you've got to account for what are the stresses and strains and loads that are put on that object, whatever it is, while it's being moved. These vessels were pretty stout. I think the walls were like 12 inches thick. I mean, this is the pressure vessel where the pressures are made for the nuclear. Now, today, this kind of move probably never be made again. Everybody today is talking about the small modular reactors where, a big old nuclear plant, you're probably seeing the last of them being built down in Georgia at Plant Pole. Other questions?
Just a quick comment on this, actually.
Yeah.
University of Illinois is trying to move a reactor right
Right.
now as we speak. Are you aware of that?
Yeah, I've seen a little bit of the PR or news blurbs on that.
Yeah. So
And
they contact us,
Yeah.
maybe I should point them
No,
to you.
It's that I think is the future, because if I can put a 100 megawatt plant or a 200 megawatt small plant in Champaign, my grid requirements become totally different than if that plant is sitting down there near Clinton. Okay, so you can totally different mindset comes into play on all of the power distribution issues that are. Everything is about, if you go back to high school, you were taught, hopefully, time and place utility. The right thing in the right place at the right time. So that's why the railroads all got built, so get things to market on time before it all spoils. Okay,
So,